So there are basically three places that you can do pH calculations for titrations. You can do them before the equivalence point, at the equivalence point, and after the equivalence point. So the first method, before the equivalence point, that is where your moles of your weak acid or your weak base are greater than your moles of strong base or strong acid. For these types of problems, you want to use the Henderson-Hasselbalch equation. So here's an example. What is the pH of a 500 milliliter 0.01 molar HCN solution that is titrated with 10 milliliters of 0.1 molar NaOH? For this, they give you a pKa of HCN equal to 9.21. So the first thing that we want to do is get our moles of each of our reactants. So our HCN will be 0.005 moles. For NaOH, we'll have 0.001 moles, and then our NaCN concentration will be 0 at the beginning, or our number of moles will be 0. We don't care about H2O because it's a liquid, so now what we can do is subtract our least number of moles. So that will be our 0.001 moles, subtract them from both the reactants, and add them to our product. So at the end, we'll have 0.004 moles of HCN, none of our NaOH, but we will have CN minus that we've created. So because we have HCN, our weak acid left over, and none of our strong base, we're going to use our Henderson-Hasselbalch equation. So this equation is pH equals pKa plus log of our conjugate base over our acid. So if we plug that stuff in, we'll get 9.21 plus log of 0.001 moles over 0.004 moles. And if we solve for that, we'll get our pH equal to 8.61. Okay. So now for our second example, we have at the equivalence point. So here our moles of our weak acid or weak base will be equal to our moles of strong base or strong acid. And for these kind of problems, you want to use an ice table that starts with the salt, or your conjugate acid or base that you're working with. So in this example, what is the pH of a 100 milliliter 0.01 molar HCN solution that is titrated with 10 milliliters of 0.1 molar NaOH? And again, we have our pKa of 9.21. So again, we want to get our moles. So we have 0.001 moles of HCN. We have 0.001 moles of NaOH also, none of this. And then we'll subtract our least number of moles. And then we'll also add that same number of moles to the other side. So when we do that, we'll have none of our HCN left over, none of our NaOH, but we will have 0.001 moles of our CN minus. So now what we'll do is set up another reaction. That CN minus is not going to just sit there, it's going to react with H2O. So when it does that, we will reform HCN, and we'll have OH minus also. And so now what we want to do, we want to get these moles into molarity before we plug that into our reaction there. So to do that, we'll get our 0.001 moles, and we'll plug that in over our total volume, which is 100 milliliters plus 10 milliliters, so 0.11 liters. And then when we do that, we'll get 9.09 times 10 to the negative third moles, or molar, I mean. So when we do this ice table, we'll have none of the HCN and OH minus at the beginning. We'll have our change of negative X on the reactant side, positive X here, and then our equilibrium will be 9.09 times 10 to the negative third minus X, and then plus X and plus X. Okay, so now we can find our Ka. So to do that, what we'll do is use our pKa. So we'll do 10 to the negative pKa, or 9.21. We'll get our Ka of 6.17 times 10 to the negative 10th when we solve for that. So now we can set that equal to our expression, which will be x squared over 9.09 times 10 to the negative third minus x, which is our reactants. So because that Ka is such a small value, we can basically approximate this x on the bottom to be 0. So we can cross that out. And if we solve for this x that we have, this x squared, our x that we get at the end will be 2.37 times 10 to the negative 6th. And that x that we got here is going to be this OH concentration that we have at the end. So using that, we can find our POH as negative log of our X concentration, or 2.37 times 10 to the negative 6th. And when we do that, we'll get 5.63. We can use that POH now to get pH by doing 14 minus our POH, 5.63. That will give us our pH of 8.37. So that is our second pH that we got. So onto the third example, after the equivalence point. So here, that means that your moles of your weak acid or your weak base are less than your moles of strong base or strong acid. And so when we have this kind of example, we want to use POH or pH. So this example states that you're trying to find the pH of 100 milliliter 0.01 molar HCN solution that is titrated with 50 milliliters of 0.1 molar NaOH. All right, so again, we want to get our moles. So we're going to have 0.001 moles here. We'll have 0.005 moles of our NaOH, and we'll have none of this. So now we want to subtract our least number of moles again. So our 0.001 moles, subtract that on both of the reactants, and add that to the products. So when we do that, we'll have none of our HCN left over. We'll have 0.004 moles of our NaOH, and we'll have our CN minus. So because this NaOH is a strong base, the contribution that the NaOH brings to the pH will be much greater than the contribution of the CN minus. So that means that we only have to count for the NaOH concentration when we're trying to find our pH. So to solve for our pH, we'll first get our concentration of NaOH as 0.004 moles over our total volume. So our total volume will be 100 milliliters plus 50 milliliters, which will give us 0.15 liters. When we find the concentration of that, we'll get 0.027 molar. So now we can plug that into POH, equals negative log of 0.027, and we'll get 1.57 there. And now we can plug that in to get our pH. It's 14 minus 1.57, and we'll get our pH as being equal to 12.42. Okay, so these are basically the 3 different ways that you can get pH calculations and do titration problems.